Alrighty, today in class we talked about Graham's law, and basically we have a couple definitions. The word diffusion, and you kind of should be familiar with the word diffusion because you've usually used that maybe in biology or anatomy, physiology. Diffusion is just particles moving from an area of high concentration and basically just spreading out. For example, if you spray perfume in a room, it'll start in one location, but it will diffuse across, and so until we get to a point of equilibrium where the particles have evened themselves out. So the term effusion is very, very specific to gases, and we talk about gases can effuse. So it is a type of diffusion, and they effuse through a small hole. For example, if we had a balloon, and a lot of times you'll fill up the balloon with helium, and the next day it is all gone, and that's because it has effused through a tiny opening, such as your car. It'll slowly leak and lose gas, and so you will have to check your tire pressure so that's effusion. So just basically gases escaping through a tiny hole. And so if we had two gases and we were comparing two gases and then they were in the same environment, meaning they were at the same temperature and they were at the same pressure with one another, then the lighter gas would actually effuse faster. Now we do know if we change temperature, a hotter gas is going to move faster, and so it would diffuse faster. So it has to do with kinetics and the movement of the particles. And so Graham's law basically takes that principle, and it is the square root of the molar masses, and we get that from the periodic table. And if you'll put the heavier gas on top of the lighter gas, if we take the square root of those molar masses, because it's proportional to its square root, then that's going to tell us how many times faster the lighter gas is moving. And lighter gases will always move faster. So it's a very simple formula, but we're going to use applications of this formula as we progress on. So our first one is just a very easy comparing two gases. So we're assuming that they're at the same temperature, they're at the same pressure, so we're going to compare the effusion rate of chlorine and nitrogen. Now these are both diatomic, so chlorine is Cl2 and nitrogen is N2. So when we do their molar mass, we do need to double it. So that's important. So I'm going to take the square root, and the heavier one would be the heavier number, and that would be chlorine. Chlorine is 35.5, but if we times it times 2, we get 71. The unit for that is gram per mole for molar mass, how many grams per mole. And then for nitrogen, nitrogen's 14, but times 2, we get 28 gram per mole. So we simply take the square root of those two, and we will get a number. And so you'll get a number, and we'll go 3 sig digs for this, 1.59. Now, it says compare. So if you were comparing something, that usually requires some sort of sentence for you to understand what that number means. It doesn't just mean, hey, just give me a number, let's make a sentence out of it. So what this is always going to tell us, as long as you put the heavier over the lighter, as long as you do that, heavier over lighter, this is always going to tell you how many times faster the lighter gas is going than the heavier. So which one is the lighter gas? Well, nitrogen. So we would say N2 is 1.59 times faster than chlorine. And so that would be our sentence for our comparison. So pretty easy formula. We just got to write the sentence if it asks us to compare. So now we're going to take this and apply it, do an application process. So now it says if carbon dioxide diffuses at a rate of 0.321 meters per second. So what we've got here is an actual speed. This is a speed going on, so how fast it's going. What would be the speed of hydrogen? So the first thing you want to analyze is, well, who's going faster, carbon dioxide or hydrogen? So we would kind of be able to tell that by looking at molar mass. Carbon dioxide being CO2, 1 carbon and 2 oxygens, is going to have a molar mass of 44 grams per mole. Hydrogen, being a very small gas, H2, diatomic, has a molar mass of 2 grams per mole. So which one's going to go faster? Well, hydrogen's going to go faster. It's going to be a faster gas. So for example, if I'm going down and I'm driving down the road and I am going 40 miles an hour and you are faster than me, you're going to have a bigger speed. If you're 2 times faster than me and I'm going 40, I would take 40 and multiply by 2, and I would get 80. So you'd be going 80 miles per hour. So if I'm looking for a faster gas, I'm going to basically take the speed of the other guy and multiply. If I'm looking for a slower gas, I'm going to be dividing. For example, if I'm going 60 miles an hour and I'm 2 times faster than you, then you would take 60 and divide by 2. So this speed is kind of in timeout until we figure out a times faster process. And so we do that by using Graham's law. So heavier, always on top if we use it this way. And so that's going to be 44 grams per mole divided by the hydrogen, which is 2 grams per mole. And I take the square root, and as I take the square root, I get 4.69. Now you don't have to write the sentence for this type, but if we wanted to write the sentence, it would be hydrogen is 4.69 times faster than carbon dioxide. And since I know the speed of carbon dioxide, so we know CO2 speed. CO2 is traveling at 3.21 meters per second. And this guy's going, hydrogen's going faster, so I need to take this speed and then multiply by the 4.69 to figure out. This doesn't have a unit here because these units cancel, so this doesn't have a unit over here. I'm going to multiply by that, and I get 1.51 meters per second. And it should make sense that, ooh, it started saving. That should make sense that it's a bigger number. It should be a bigger speed because it should be going faster. So if I'm looking for the faster gas, so looking for the speed of the faster gas. Now faster would mean it's the lighter one. So looking for the speed of the faster, lighter gas. I'm going to take the meters per second that's given, meter per second of the slower gas. So always start with the meters per second, and you're going to multiply by the answer to Graham's law. I'm just going to put GL, answer to Graham's law. So that's what I did. I took the meters per second and I multiplied by the answer I got from Graham's law. So I just have to think. If you watch a lot of YouTube videos and things, you're going to get trapped into a lot of physics formulas, and there's lots of different formulas out there, but if you'll just use this one formula and then think, Graham's law makes complete sense. So what would we do if we're looking for the slower speed? So if we're looking for the speed of the slower gas, so if we're talking the slower gas, that's going to be the heavy one. So if I'm looking for the top guy's speed, so the heavy gas, well, I'm going to also take that meters per second, but I'm going to take the meters per second of the fast gas. It would be given to us in the problem. And I'm going to divide by the Graham's law answer. So up here, if this had been the speed of hydrogen and I was looking for the speed of carbon dioxide, I would have taken this 0.321 and I would have divided by 4.69. Okay, so that we would have got a smaller number because we should be getting a smaller speed. So hopefully that makes sense to you. Alright, sample problem number 3. An unknown gas diffuses 4.22 times slower than hydrogen. What is the molar mass of this unknown gas? And so we can't use the periodic table because we don't know it, so we're going to have to use Graham's law. Now it says our unknown gas diffuses 4.22 times slower than hydrogen. So that means that hydrogen is the fast gas and hydrogen is 4.22 times faster. So again, Graham's law. So this 4.22 times faster is going to go over here. It doesn't have a unit. And we got to decide, is it the unknown that's the fast one, or if it's hydrogen, because it does matter. It's kind of easy with hydrogen because it's the lightest gas we have, so you can't have a lighter than hydrogen gas. But if it hadn't been, you always know that your slow one's on top and your fast one's on bottom. And so we are looking for the slower guy, so this is going to be where our X is going to be. Hydrogen's molar mass is going to go here. Hydrogen just so happens to be 2 grams per mole. Remember, diatomic. Alright, now I got to solve for X. To solve for X, when you've got something with a square root, I'm going to switch colors here so you can see, we just basically square both sides. When you square both sides, when you square something that's under a square root, it just makes the square root go away. I'm going to get rid of the units for a second. So we're just going to get X over 2 because it just takes that away. But then I do have to square this side over here. And so I would suggest you kind of keep that whole number running in your calculator or write it down. Sometimes they'll come out. So that's what I got there when I squared that. So now, how do you get X by itself? Well, you just got to multiply both sides by 2, right, to send 2 over to the other side. And so then we can do 3 significant digits. I got 35.6 grams per mole. If we were looking for the lighter, slower, faster gas, our X would be on bottom, but it would work the same way. All right. Under the same conditions of temperature and pressure, so we're just saying that our gases are in the same container about the same time. So I decided just to use carbon dioxide and hydrogen because we'd used that one just a second ago. Now notice we don't have a speed, we have a time. So time works a little bit different than speed. For example, if I'm driving to Mount Pleasant, it's probably going to take me somewhere between 45 and 50 minutes going at the speed limit of 75 miles an hour. But if you are faster than me, then you may get there around 30 minutes. Okay, so if you're faster, you're going to have a smaller time. If you are slower than me, you're going to have a larger time. So they're kind of opposite from that meters per second because the meters per second is the speed. So you have to kind of think with this one. Alright, so I'm going to go back. I have to compare them. We had carbon dioxide, which was that 44 gram per mole. And we had hydrogen, which was that 2 gram per mole. So if I go back to Graham's law, that was at 4.69. So I just got to decide what am I going to do with that 4.69. So let's see. They've been giving us the speed of carbon dioxide. It takes 32 seconds for it to get out of whatever container it's in, to effuse, to get through a tiny opening. So is it going to take hydrogen less time or more time? Well, hydrogen's faster, so if you're faster, it's going to take you less time. So that tells you right now what you're about to do. You're going to always start with this, like a while ago we started with the meters per second, so always start with this and use that second. We're going to take that 32 seconds. We're not going to multiply, because if we multiply we're going to get a bigger time. We want a smaller time. And we are going to divide by the 4.69. And we'll still, this again doesn't have it, so I get 6.82 seconds. So time is a little bit different. So if I want the faster gas time, then I'm going to take the time given of the slow guy, and I'm going to divide by Graham's law. If I'm looking for the slower gas time, see how it's opposite? And it should make sense that it's opposite. So you're going to take the time that's given. We're not going to get into the physics formulas where you find time of the faster gas, and you're going to actually multiply by Graham's law, because slower time we want a bigger answer, we multiply. So if you think through it logically, it should make sense to you. Alright, last problem here, and I just want to show you this one because it's kind of misleading. I decided not to put one like this on your test, but I just wanted to show you. An unknown gas diffuses at 0.25 times as fast as helium. Well, if you're 0.25 times as fast, you're really not. You're like a fourth of the speed. So you're really not faster, you're really slower. So another way we would say that is helium is 4 times faster. Why? Because that's a quarter of the time. Think money, that's a quarter of the time. So it would take 4 of them. So helium is really the faster gas here. It's 4 times faster. You don't really want to use fractions, so it doesn't help very well. So let's start here. So we really kind of want to be in whole numbers. So now I could put that 4 over here. And we've got helium. Helium is faster, so helium will go on bottom. That's 4 grams per mole. Unknown gas, we've got X on top again. So what are we going to do? Well, like before, we're going to square both sides. When you square this side, square root goes away, so you have X over 4 now equals 16. So now multiply both sides by 4, and your X is 64 gram per mole. Alright, that's pretty much Graham's law. So now we're going to move to the real gas law. And I'm going to give you this formula on the test because it's going to look real intimidating. But we talked about ideal gas and how an ideal gas, so to speak, doesn't have a mass, and it does have a mass, but it doesn't have a volume. And then there is no attraction between molecules, no intermolecular force. But we do know that both of those truly do exist. So the real gas law, created by van der Waals, which was a physics professor, he took into account the fact that there is volume, and he took into account that there is intermolecular attraction going on. So this beautiful formula you're about to see is the real gas formula. It's what's kind of really happening with the gases. And so we say, how far does it deviate from the ideal gas law? And so it helps us see how far we are. I love the ideal gas law, and then once you see this formula, like, okay, I understand why we just use the ideal gas law, because a lot of times we get pretty close to the right answer. Okay, so pretty much that's what's going on there. Here's our beautiful formula we got. You can see it's very similar to P equals nRT. See the P and the V, but we've got a correction here, and we have a correction here. The correction here is correcting for those intermolecular forces, and the correction here is correcting for the volume. So it's technically P equals nRT with corrections to it. So you don't have to memorize any of this, but this does explain what those little A's and those B's are going on. We're going to see those values, and I'm about to manipulate this formula with you. And I will give you the manipulated version on your test. So first off, we want to see what the ideal gas law says. So it says calculate the pressure exerted by 84 grams of ammonia, and ammonia is NH3. We saw that guy in the lab. It says it. In a 5-liter container at 200 degrees Celsius using the ideal gas law. Well, the ideal gas law is PV equals nRT. So we're looking for pressure, and I should say on these we're looking for pressure in ATM. Okay, so P I don't know. V is 5 liters. N stands for number of moles, so that 84 is not going right there, so I need to convert 84 grams of ammonia, and I need to convert it to moles. And we hopefully at this point in the game are good at that. 1 nitrogen, so 14 plus 3 is 17. We can just take 3 significant digits. I'm okay with that. I'm trying to see where I wrote this down. I got 4.94 moles of ammonia. Whoa, does that like it's doing in class. Hold on, moles. No, just going to have to go there. Moles of ammonia. Alright, so I'm going to put over here 4.94 mole ammonia. And because I do want an ATM, then we're going to use the 0.0821. Also give you that on the test. Liters, atmospheres, mole, Kelvin. And then our temperature was 200, but we have to add 273. So we get 473 Kelvin. Alright, so we multiply this side, divide by 5, and then we can do 3 sig jigs, so we've got 38.4 atmospheres. So if this gas, this ammonia, that's 84 grams of ammonia sitting at 200 degrees, were ideal, it should be taking up 38.4, well, not taking up, but having a pressure of 38.4 atmospheres. So we're about to see how far it's deviating, because its temperature is not in an ideal situation. So we're about to see how far it's deviating. And because it's hotter, it's why it's deviating. Alright, so this is where this beautiful formula comes into play. So we need pressure. That's what I'm looking for. So again, I'm going to give it to you manipulated, but I'm about to manipulate it here with you as I did in class. So I'm trying to get P by itself, and we think about PEMDAS, or please excuse my dear Aunt Sally, this order of operation to solving. So our first order of operation is to take this that's being multiplied and put it over on the other side. So this is going to go over here. That N is times that B, and that would send that guy over. And then do you see how this is being added over here? So then to get all this beautiful stuff over there, I would subtract. So this is how the formula really looks. And now I get to plug. So now I've got pressure, that would get rid of this. Pressure now equals this minus this. I will tell you, all you're really going to be doing on the test is plugging. But I would tell you to do it in 2 separate steps. I would tell you to do this, get an answer, do this, get an answer, and then subtract those two. And that's what my suggestion to you. So I'm going to start way over here. Alright, moles. We just figure out what that mole would be. And I'll be nice on here. I won't make you put all the units, because you're going to have lots of numbers going on, so it gets a little confusing, especially with the A's and the B's. See those beautiful units there. So we're going to have, on P equals and RT, I want to see units, but on this real gas law, I'll be okay. So we have 4.94, that's the N, times the R, 0.0821, times the temperature, looking just like we did a while ago, 473. I'm wanting to put a unit on there, divided by the volume, which was 5. Now this is where we got to be careful. Those two need to be multiplied together before they get subtracted. So that's going to be important. So I'm going to put them in a parenthesis with one another. So 4.94 times, and the B, if I look up here, B equals 3.71 times 10 to the negative second. I'm going to put it in regular numbers because I don't really like that scientific. So 0.0371. So there's that side. So I would suggest you get an answer. So I would have you work that, kind of work that, then subtract, then divide those numbers. Let's see, I wrote that down somewhere. I would kind of keep that going in the calculator or write it down. 39.82715687. Isn't that pretty? Alright, then we have the other side. Minus N squared, that would be 4.94 squared. That's where students make a mistake. They forget the square. Times the A, and the A is 4.17, divided by V squared, which is 5, which is the volume, squaring it. So then minus, I would do all this beautiful stuff in the calculator. I got 4.0705204.8. And then subtract them. Again, calculators are nice. You can take that number, subtract that number, and get an answer. We can round to 3 significant digits like we did earlier. We're going to get 35.8. If we got rid of all those units, because it's pressure, you would see that it is atmospheres. So this is what the gas is really doing. It's only doing 35.8 pressure, atmospheres of pressure, where we thought it was going to do 38. So the last part is, what's the percent difference between the two? So it's like percent error. So to find the percent difference, you're going to take the ideal answer minus the real answer divided by the ideal. It's just like percent error in lab that we've been doing. So ideal minus real divided by ideal, and then times 100 to make it a percent. So our ideal answer was 38.4 atmospheres, we can put units on this one, minus the real answer, 35.8. So we're seeing how far it's deviating from what we thought it should be. It's kind of like giving the gas a grade. You should be getting this, you're only getting that. And then divide by 38.4, and we times it by 100 to get it to become a percent. And I got 6.77%. So it's deviating about 7% off. And that's the ideal gas law. You have 2 of those on your homework, and you will have 1 of these on your test, so just let you know. Alright, hopefully this makes sense to you, and come see me if you need any help.